So, what happens when you have a matrix such that the eigenvalues are repeated? Well, let's find out. Let's first start off by finding the eigenvalues. As we can see, our eigenvalue is 2, but this solution has a multiplicity of 2. So, what do? If we already know our formula for the general solution of this differential equation, but it looks like we'll only be able to generate one solution. That's not enough solutions to even generate a general solution. So, what do? So, if you remember from one of my previous videos, what happens if we have a differential equation like this that has a repeated characteristic root? So, this differential equation leads to this characteristic equation, and we find that the root -2 is repeated. So, well, it's pretty simple. We just take c1e to the -2t plus c2. Then we stick in this extra t here. Then we stick in the e to the -2t, and then that would be our solution to our differential equation. Simple like that. Well, with repeated roots, we do something similar, where we have x is equal to c1, first eigenvector. I don't really know how to draw the eigenvector symbol. Plus, well, then we have c2. Then we have that same eigenvector. Actually, we don't really need the t. Then now we add this thing called a generalized eigenvector. And then this generalized eigenvector allows us to generate enough solutions for a general solution for this matrix. So, in order to find the generalized eigenvector, first of all, we must subtract 2 from the a and d entries again. So we have -2, -2, 2, and 2. And then we need to find the original eigenvector, or eigenvector 1. Here we can find that the ratio between 2 and 1 is just 1, 1. Then we need to stick in a negative sign. And then in order to generate this generalized eigenvector, what we need to do is take this matrix over here, and we need to multiply this unknown generalized eigenvector so that it equals the eigenvector that we know already. So we can reduce this to row echelon form. So we have -2, -2, 2, 2, 1, -1. So in order to do this, we can get rid of this bottom row. So -2, -2, 1, 0, 0, 0. Then after that, we can just multiply the first row by -1/2. So 1, 1, -1/2, 0. So we get a plus b equals to -1/2. So we could just plug in any number for either value. So I'm just going to plug 0 in for a. So that would mean that obviously b equals -1/2. So our generalized eigenvector is equal to 0, negative 1/2. So then our general solution can be C1, 1 negative 1, e to the 2t power, plus C2, 2, 1 negative 1, plus 0, negative 1/2, e to the 2t. So our final scenario is complex roots. So what the hell do you do when you have something with complex roots? Well, let's find out. So let's take our eigenvalues first of all. So we have 2 minus lambda, negative 2 minus lambda, plus 8 equals 0. So we get this 0. So we get lambda squared plus 4 equals 0. And as we already know, this is a complex root. Well, shoot, what do we do? Well, let's start off by subtracting, let's just subtract the positive 2i. If we subtract the negative 2i, it'll get the same solution, so let's just start off with the positive 2i. So 2 minus 2i, negative 4, 2, negative 2, minus 2i. Then we can find the eigenvector for 2 minus 2i, which is 2, 1 minus I. Well, as usual, we could just plug this into our matrix solution formula. So let's just say that x equals, we have C1 e to the 2i power times 2, 1 minus I. Well, we can split this into multiple parts. So we have e to the 2i, which our identity should say is equal to sine 2t plus cosine 2t times I. And then this 2, 1 minus I is equal to 2, 1 plus negative I, 0, 1. So we can multiply these together and we should get 2, 1 I sine 2t plus 0, 1 sine 2t. And then when multiplying the cosine, we get 2, 1 cosine 2t minus 0, 1 I cosine 2t. And then we can group the non-i's together, so we get 0, 1 sine 2t plus 2, 1 cosine 2t. And then we can add C1 because the constant doesn't change. So that's our first solution. Then the solutions with the imaginary numbers, we can use x2 of t is equal to C2 of, well, let's see, 2, 1 sine 2t plus 0, 1 cosine 2t. then since I is kind of like an arbitrary constant, you can include I in the C2 like I did. And then these are solutions to this matrix. So some applications of these weird matrices are Lotka-Volterra equations, which is basically another word for modeling predator-prey relationships with differential equations. So not only can you describe predator-prey interactions with differential equations, you can also use matrices to describe these. And you can even use matrices to help you solve for x and y. Like, will the predator-prey relationship look like this? Will it look like this? Well, it depends on the equations. And matrices can help you solve them.